Okay, in the previous video, I said there's three basic approaches to dealing with the Dirac Delta function, the way I'm going to talk about it. So this video is about this first approach. I'll just call the Dirac approach. More or less the way Paul Dirac originally started it, and the way undergraduate engineering textbooks talk about it. Most of the engineering textbooks have this kind of thing. You start out with this function like this. We'll call it a pulse. This is a box pulse. That the area, where do we go here? The area under that curve is 1. And you keep narrowing it down, but keeping the area to 1 so that you ultimately get this infinite spike. And they'll usually denoted with this arrow up here, which means it's 0 everywhere, infinite or undefined at 0. So it has this property. And if you integrate over it, it still integrates to 1. And this is pretty much where Paul Dirac started. These are the two defining properties. And from those, you derive what else you need. And here was the sort of bad part or non-rigorous part. You use normal calculus to derive properties from these two properties, pretending like this guy is a normal function, even though he's not. So this infinity here. An alternate sort of motivation, you might want to say, or maybe just an intuitive insight. Take the unit step function, which is this guy here. It's 0 for t less than 0, 1 for t greater than 0. What would its derivative look like? Well, it's flat everywhere except at 0. So its derivative, if we call its derivative the Dirac delta function, it's 0 everywhere that t is not 0. Kind of like infinity straight up, slope straight up at 0. And if you integrate this guy, it integrates to 1, as long as your integral contains t equals 0. So again, just these two properties, and from there, we go off to the races, maybe. Here's the other big property. Here's a property we really want, so-called the sifting property. If you had a function already, and you put the Dirac delta function in an integral with it, integrate over the entire real line, what you get is this function evaluated at 0. You just mapped a function to a number. And in this advanced engineering math book, the one that's considered kind of more rigorous than others, all it says is, well, that's plausible. And just says, and here it is. Here's the property, and it's plausible by something up here. It doesn't really derive it. I tried to derive it. I think I did okay. This is what you'd have to do, just pretending normal calculus works. I'm not going to go through this, so be relieved. But you employed the extreme value theorem of basic elementary calculus. Go back to your calculus book. You can look up this theorem. You can look up the squeezing theorem. And you ultimately get there, I think. At least this is my derivation. And by the way, I checked it out with AI, and it said it's okay. But that's kind of painful, I think, to come up with what's one of the more key properties of the Dirac delta function. So that's about as much as I'm going to talk about that approach until a little bit later. So if that was too hard, maybe we ought to just use distribution theory. So let's consider that, and I'll save that for the next video.